Today we study ESA22H, driven damped harmonic oscillator. Driven damped harmonic oscillator is a damped harmonic oscillator at which a driving force is applied, to which the driving force is usually a sinusoidal function. It doesn't have to be the same as this function, but for simplicity, we apply a sinusoidal function. We recall the differential operator for the damped harmonic oscillator, and simple damped harmonic oscillator is expressed in this form. Here omega 0 is a square root k over m. That is the characteristic frequency for the corresponding simple harmonic oscillator that does not have this term. And we focus on the driving force applied to a damped harmonic oscillator whose parameters satisfy the underdamped motion. That means square root of k over m is greater than b over 2m. We call a solution of this equation of motion is a particular solution, and we call xh, that is the solution corresponding to a damped harmonic oscillator. That means that this right-hand side is 0. That is, we call this one to be a homogeneous equation. So this F0 cosine omega t, this driving force is absent. And what we want to find is x satisfying this equation. And I'd like to know how to express this general solution x for the driven damped harmonic oscillator. We remember the solution for the damped harmonic oscillator without any driving force is expressed as a product of the exponential evanescent factor multiplied by the oscillating factor. We remember the oscillating factor is periodic, but the whole function is not periodic anymore because of this exponential factor. The frequency of this damped harmonic oscillator solution is a slightly smaller than the characteristic frequency or angular frequency for the corresponding simple harmonic oscillator. We named a solution. It doesn't have to be a general solution. A solution, suppose that we have found a particular solution that is a solution of this full expression, including driving force. We call xh the general solution for the corresponding homogeneous equation that does not have this driving force. We can add these two equations, the left-hand side and left-hand side, right-hand side, right-hand side. This one, the result is the same. So we have a particular solution, and if we know the homogeneous solution, the solution for the homogeneous equation, the sum of them, in which we have two arbitrary parameters, this is the general solution for the driven damped harmonic oscillator. In general, as time goes by, this solution for the corresponding homogeneous equation disappears completely. It becomes negligible as t goes to infinity. However, when the time is not small, we have a transient effect, sudden rise up of the solution. So the neglection of this corresponding homogeneous solution is allowed only if time is large enough. So to avoid the transient effect that appears significantly at small t, we consider the case in which t is very, very large. Then we say it is free of transient effect, and the region is a little bit stationary solution. Consider driven damped harmonic oscillator. We keep on considering this. Why don't we introduce a particular solution, whether this one satisfies the relation or not? If we consider a frequency that is different from the driving frequency omega, given in here, this is driving frequency. If I use a different frequency for the trial sinusoidal function, the answer gives final answer. For example, xp dot is minus a sine a omega prime sine omega prime t plus delta, something like that. Double time derivative, so minus a omega prime squared cosine omega prime t plus delta. That means the right-hand side is function of omega cosine omega t. Left-hand side is a linear combination that they are all periodic with the angular frequency omega prime. So it is impossible to have a trial solution to be satisfied by this equation. The only possible way is omega prime is the same as omega. Therefore, why don't we introduce cosine omega t with the arbitrary undetermined amplitude? If we substitute this one for the x in the equation, the left-hand side becomes this. Finally, we find there is an additional phase that cannot be matched with the right-hand side. Therefore, we expect that there must be some difference in phase between the driving force and the particular solution. Additional way, we have a final trial with the same frequency but a little bit different phase. If I use undetermined phase constant with minus delta, our additional phase difference cancels. Remember, I did not introduce the phase difference, but the result on the left-hand side was positive. That means if I introduce a phase in opposite sign, then the final result does not have this phase dependence. Let's see. We have this first order time derivative, second order time derivative, and substitute everything to the equation. Where is the equation? This operator is applied to this. Finally, we obtain the linear combination of sine, cosine, and sine. We remember m x double dot plus kx plus bx dot. They are both cosine. Why? Double time derivative will bring in minus omega squared cosine. So minus m omega squared cosine. Kx, simply k. So k minus m omega squared cosine omega t minus delta. And here, derivative will bring in minus omega b. And cosine becomes sine. We remember we can add these two by, for example, a cosine theta plus b sine theta. Then we pull out the square root a squared plus b and a over square root a squared b squared cosine plus b square root a squared plus b squared sine theta, something like that. And we apply the addition formula for the sinusoidal functions. And finally, we can find it is a cosine. Cosine, okay? Cosine, cosine. When we define cosine to be this, we remember omega 0 squared is k over m. So cosine, cosine, sine, sine. That is a cosine, this one and this one. In here we have found this, the delta dependence cancels exactly. Therefore, this particular solution is the same as the right-hand side, that is f0 cosine omega t, as long as this amplitude is matched. Phase dependence matches and amplitude matches. So this will be the final result for the exact solution. We remember the particular solution plus the arbitrary solution for the corresponding homogeneous equation is another particular solution. So a particular solution is not unique. However, in the limit as t goes to infinity, this numerical dependence of the difference of any two different particular solution is numerically negligible. And this is a way to find a particular solution, and this particular solution is analytically not unique, but numerically almost unique. Okay, that's it for today. Thank you.